Hello, welcome to another Stat 510 video. In this video, we're going to talk about expectation. So, probably shouldn't be a surprise. The first thing we're going to talk about is the definition. That is the definition of the expected value of a random variable, in this case, some generic random variable x. I should say right away that expected value is what we're defining here, but this has sometimes goes by other names. For example, mean, and later in a different video, we'll see that we might call this particular expectation the first moment. But that's not super important. That's just some nomenclature. So the middle line here is the definition. And so the first equal sign is sort of just the generic notation. But then we have to consider two different cases, actually. And that notation represents either case. But when we get down to the specifics, we have to consider, are we dealing with a discrete random variable or a continuous random variable? So here, x is discrete. So this is a probability mass function. And then in the other case, we have x is continuous, which would mean that this is a probability density function. Okay, so the last thing I want to say about the definition is that all of this, everything on this line is just notation. So all of these funny looking symbols could all be placeholders for this notion of expected value. Like for example, mu and mu sub x we'll use interchangeably. Sometimes we'll do mu sub x to make it very clear that we're talking about the expected value of the random variable x. Sometimes we'll drop that subscript when it's clear from context what we're talking about. But just do know that all these things mean the same thing. Sometimes folks get a little bit tripped up if they see a mu when they were expecting a Blackboard E, but it's all interchangeable. Okay. So really brief example here. So I believe this is a distribution we saw from a coin flipping example previously. So on the left-hand side here, we have the probability mass function, which is very simple. And so we want to find the expected value. So the very first thing we do is, I'd say when we're doing this equality here, we're simply applying the definition, and then everything else is just calculation. I would note that because we're dealing with a discrete distribution here, this f of 0 is the probability mass function at 0. In other words, this is exactly the probability that x is equal to 0. And that's what expected values do. You take probability of value times value and add all those things up in the discrete case. And then if we do a little bit of math here, so I think this works out to be, let's see, 0 times a fourth plus 1 times a half plus 2 times a fourth. And coincidentally, we get a really unfortunate answer here, which is 1. That is the expected value. I just want to note one really common mistake folks encounter when they first do these types of problems, which is that anytime you get an expected value of 1, you should be scared, because what that means is, oh wow, that's interesting. There's a possibility that you simply forgot to put that x in the calculation, and then if we add up all the PMF at all the possible values, well, of course it's 1, because that's how probability works. So just something to be aware of there. This is the correct expected value, which should be pretty obvious if we just look at this PMF. It's kind of in the middle there. But that is an opportunity to go check your work, I would say. Okay. Another quick example here. I'm not going to work this one, but this would be an example of calculating an expected value for a continuous random variable. So here we get an expected value of 1.5. Again, sort of no surprise given the distribution. Notice again, this is not equal to 1, so we probably didn't make the mistake. But again, if you got 1 for some reason, go back and make sure that you have that x right there. That is, you're doing the definition. Okay, not too difficult. So now a couple examples that maybe get to the intuitions of some of these things a little bit. So here I have an example. So suppose we're going to flip a coin. Here I have a coin. It's a silver dollar. And what we're going to do is if it's heads, I'll give you $100. But if it's tails, you have to give me $5. So I wrote out the potential PMF for this up in the top right hand corner. So with probability half, you give me $5. With probability half, I give you $100. And so would you take this bet? So a lot of times in gambling situations, and gambling being really important to the foundations of probability, I'll leave out my opinions on gambling, but this example might sort of get you to think about some of the things I would think about when gambling. But so we would say that a bet is fair if the expected value is 0. So the expected payout to both of us would have to be 0. But clearly, in this case, you have a much greater expected value than me. I did the math here. You have an expected outcome of $47.50. So this seems like a pretty good bet. Like you should sign up for this immediately and maybe repeatedly. But I want to caution you. Ignoring this PMF for a second. If I didn't tell you that was the PMF, because I didn't actually say that was the PMF. I said it could be the PMF. So that PMF assumes that this is a fair coin. It is, but I didn't give you any proof of that because I didn't show you the tail side. I only showed you the heads side. I'm really bad with mirrors. So if I offer you this bet and I don't show you both sides of the coin, your first reaction should actually be, wait a second, this is outrageous. Something's wrong here. I'm being tricked. But if I then show you both sides, then you should be a little more reassured. But even then, maybe the coin's weighted in some way, and you shouldn't take the bet. But so what I'm saying is, if you see an expected value like this, and I'm offering you that potential bet, something is probably not right there. For example, I've never actually been to Vegas and I never gambled. So I don't know. I think this is a true statement. There's no gambling inside of a Vegas casino for which the player, you, would have a positive expected value. I do believe the house always has a positive expected value. And that's kind of the expectation. So if you see something outside of that, you should be skeptical of it and sort of ask yourself, what am I missing here? So what I was saying is this, if the coin is fair. So, and again, this here assumes a fair coin. And again, this is for, I should have labeled this earlier. This is for heads. This is for tails. So we could ask ourselves a question, which is how bizarrely weighted would this coin have to be to make it a fair coin? So let's arbitrarily define this to be P and this to be 1 minus P. Space in there. Okay, so so those add up to 1. So, and then what we want to do is solve 0 equals expected value of x. So when it's heads, you lose $5 with probability 1 minus P, and you gain $100 with probability P. This works out to be something like 105P minus 5. Is that right? I think that's right. And so if we solve this equation, it's a fair bet if P is 1 over 21. And then it's fair, but whether or not you play that game is a different story. But yeah, so that's a little bit about coin flipping and gambling. I'm obligated to talk about these things as a statistician. Okay, another interesting example. This is called the St. Petersburg paradox, so you should already know that it's going to be something funny here. So what I'm going to do is I'm going to flip a fair coin this time. I'm telling you it's fair, so, heads, tails, equal probability both sides. And I'm going to flip until tails comes up. So I could get tails, or I could get heads, tails, or heads, heads, tails. But basically, when I flip and I get a tails, that's when it stops. Otherwise, I keep flipping. So what's going to happen in this game is I'm going to pay you. So, and your payment is going to be 2 to the k, where k is the number of times I flipped the coin. So if I flip the coin once and it comes up tails, it stops, I give you $2. If I, so something like, 2, if it's heads, then tails, I would pay you $4. If it's heads, tails, that would be $8, and so on and so forth. So the question becomes, if I'm going to have you play this game, how much do you pay me for the opportunity to play this game, right? So something we might want to know is, well, what's your expected winnings? That is, how much money are you going to win on average? So we're going to define a random variable x, which will be the money that you win. Okay, so now let's calculate the expected value. So you win $2 with probability half, plus you win $4 with probability a fourth. I'm not going to go through the details of how that probability of 1/4 comes about, but it's not too hard to figure out. Plus you have a 1 in 8 probability to win $8, and so on and so forth. And looks like that's going to be 1 plus 1 plus 1 plus 1, and this keeps going on. And we get infinity. It's interesting. So, in other words, we have an undefined expectation. And this is something that comes up from time to time. An example of this would be the Cauchy distribution. But then bringing it back to the original question, so on average, you're going to win an infinite amount of money. So you should be willing to pay what? Any finite amount? I mean, what's what's $100 to win on average infinite money? Well, okay, but that's not how averages work, right? You only get to play the game once. So even though the expectation is infinite, one realization of this game is not going to bring you anything near an infinite amount of money. I should have noted you can look up the probabilities for getting past a certain number of rolls and how much money you could get there. Also, I don't have an infinite bankroll. So even if I kept flipping and flipping and flipping and getting heads, at some point I just want to be able to pay you. So you don't want me or basically any institution that I know of on the other side of this bet, because they won't be able to pay you if you get the infinite if it keeps coming up heads, at some point they just won't be able to pay you. So yes, the expectation is infinite, but you're not going to get infinite dollars out of this game, so you shouldn't pay that much money to play it. I'd pay $2 to play this because I don't get my money back. That's a lower bound. I don't know what my upper bound would be. Maybe $4. I don't know, but I wouldn't pay a ton of money to play this game. Okay, so we've talked about how to calculate the expectation of a random variable. Now, statisticians are ultimately very lazy creatures. We want to do as little work as possible. I think this makes us very normal, frankly. So there's a theorem called the rule of the lazy statistician. And what this says is, if you have some random variable x and you know its distribution, and you define some new random variable y to be some function of that random variable, then this is how we can calculate the expected value of y. To do so, we use the rule of the lazy statistician, which basically says to find the expected value of r of x, you simply find the expectation. Well, here, I'm going to write out the definition, and I'm going to try to do a nice, there we go, that's better. Okay, so in the discrete case, so this is x discrete, and in the continuous case, okay, so why is this interesting? Why is this being lazy? Well, what this says is that to find the expected value of y, we can simply use the distribution of x. So, like in the discrete case here, it's the sum of r of x times f of x. So even though we're finding the expected value of y, we're using the distribution of x. Why is that being lazy, and why is that interesting? Well, because we don't have to find the distribution of y. That's pretty nice, right? If you recall, finding transformations of random variables is sometimes not particularly fun. Okay, so quick example of that. So here we have x is a uniform random variable, and I define y to be e to the x. So that's going to be, that's r of x here. That is the function of the random variable that we know about. Recall that for a uniform distribution, in this case, the PDF here would be 1/2 for 0 less than x less than 2, something like that. Okay, so now I want to find the expected value of y. Well, by definition, what I would have to do is this. And I'll put a y there to be very clear. So this is the PDF of y. And again, this is just by definition. Okay, so that would be the definition. But that would mean to go further, I would have to find the distribution of y. And I don't want to do that. So instead, what I want to do is be lazy. Okay, so I'll use the rule of the lazy statistician. No, 0 to 2, right? So e to the x times the PDF, which is 1/2 dx. All right, and then some calculus happens. I have it on my notes here, so it's something like 1/2 e to the x evaluated at x equals 2 and x equals 0. And I think that works out to be something like 1/2 times e squared minus 1. Okay, and this is us being lazy. Wonderful. Cool. All right, so that was rule of the lazy statistician. What's next? Okay, so often we're going to be dealing with more than one random variable at a time. So here we have x1 through xn that are random variables, and we have a bunch of constants. So if I want to take the expectation of the sum of those constants times the random variable, so this big linear combination of the random variables, what we end up with is essentially we can move the expectation inside of both the sum and the constants. So we get something like this. Oh, not like that. And generally, we refer to this notion as linearity of expectation. Okay. Now, in that, we didn't use anything about the distributions of those xi's, and we didn't use anything about the relationships between the various xi's. So we didn't need independence. Now, if we add on independence, we get something else, which is that if we look at the expectation of the product of these things, we can now move the expectation inside of the multiplication. And again, we can only do that because we're dealing with independent random variables. Okay. All right, one last example to wrap up this video. Okay, so let's say I define x to be a binomial random variable, and it has parameters n and p. And I ask you, what is the expected value? Well, we could apply the definition, plug in the PMF, and then we kind of throw our hands up and say, "Ooh, that's some math I don't want to do right there. I don't want to do that." So there's two ways we could proceed. There is the really lazy way and the somewhat clever but also lazy way. So let's talk about the actual lazy way to do this. Just look up the answer. Just look it up. Pick up a random textbook, this one for example, and maybe go to the back and find that table that surely exists there that lists, it lists expected values and variances for well-known distributions, parameterized in this case by n and p. And then, generally the means and variances are functions of those parameters. Isn't that nice? And you can just look them up. Wikipedia, they're all there. It's right there in that little sidebar on the right that has all the information about the distribution. The Wikipedia pages for probability distributions are absolutely wonderful. Okay, so in this class, we live in the real world. We can just look these things up, unless you're specifically asked to derive it. So now I'll do the lazy but not as lazy thing. So what I'm going to do here is, instead of working with the binomial, I'm going to work with Bernoulli's. So what I'm going to do is define x is going to be the sum of a bunch of xi's, I equal 1 to n. And in this case, xi are Bernoulli random variables with parameter p. Now, it turns out that x, as defined here, is also binomial with parameters n and p. How you would prove that is something we would look at a few videos from now when we talk about using the moment varying function. But for now, we'll just take that as known. So then what I can do is say, well, the expected value of each of these xi's, what is that? Well, again, I could look it up, but it's also very easy to calculate because there's only two possible values. So it takes the value 0 with probability 1 minus p, and takes the value 1 with probability p. So the expected value is p. Wonderful. Okay, so then the expected value of x is equal to the expected value of the sum of the xi's. But then by linearity of expectation, I can put the expected value inside the summation And we said that each of those was p. So we have the sum of p n times. So that's n p. And that should be, oh gosh, my face is in the way. And that should be no surprise. If you've seen the binomial distribution before, you know that that is the mean. Okay, that's it for this video. If you made it to the end, good job, and I'll see you in the next one.